All right, so in Module 21, we looked at what made functions unique from each other, and we talked about the idea of a function signature, including the name of the function and the data types that were its parameters. Now we're going to look at a slightly different topic, but very familiar, very similar, called function prototypes. And the goal of function prototypes is allowing us to define or declare our functions in any order by giving the compiler a little bit of a hint as to what to expect when it actually sees the full definition of our function. So function prototypes are covered in section 6.8. And it really goes to the problem of how do we declare or where do we declare functions. So previously in the modules before, we've always said that when we use a function, when we call a function, we must have already had the full definition or the full programming code written in our source code above it, or at some point before in terms of the way the compiler will see our functions. And that's okay when you only have a few functions. It ends up, with main all the way at the bottom of our source code and our helper functions towards the top. And that works fine unless you start to have lots of functions. And if you have a lot of functions, those functions may start to call each other. And after a while, the constraint that you must actually define a function before you use it becomes more and more difficult to get right. And in certain occasions can almost be can actually be impossible in the case of where one function calls another and another function calls the same one, so a circular dependency between these functions. So what function prototypes allow us to do is to declare, not define, but declare a function before we actually go about writing all of its code. The function declaration or the function prototype will contain enough information for the compiler to know how someone could use this function, namely its signature. Right? And so when the compiler sees this function prototype, we're allowed to call the function, and the compiler can basically verify that we're using the function correctly, even though it might not have already seen the full definition, the full code of the function itself. So on this slide down here, we see what the relationship would look like. In any previous example, if we had a main function, it was going to use this myFunction1, and actually there should be 2 there. All right, if we were going to call myFunction1 or myFunction2, we would know that the definition of the function, whatever that might be, would have to be above it, would have to be above main. Now what we've done is we've put an actual function prototype above it. All right, so above main, we've got the return type, the function name, and the parameter list, followed by a semicolon. Right? So there's no full definition, there's no code behind function 1 or function 2 just yet. When the compiler starts to read from the top of our page, it's going to see these function prototypes, and it's going to say, okay, well, if any code that I see uses a function called myFunction1, and it contains one integer parameter, and it's written in such a way that a double could be accepted as the return value, then it's okay. And so when the compiler moves down to main and starts reading this, it looks at the usage of myFunction1 and myFunction2, and it says, okay, that's fine, because the prototypes say that there will be a function declared like that. Now, writing function prototypes does not absolve us from actually writing the full definition, of course. These do not help us. And in fact, if we don't have the definition, then we'll end up with not a compiler error, but what would be called a linking error. The linker is the second phase of a compiler. We might have talked a little bit about this very early on in the list of modules. The linker actually does a final phase of compilation and builds your executable, and it does so with different programming units. Some of your programming units would be your functions. So what happens is that if we left out these definitions completely, so if we just took these out, we would get a linking error saying, hey, you know what, you defined myFunction1, you told the compiler that you would have a definition, but now it's an undefined symbol. So here we've got the full function definition, and what's important to note is that everything has to match up exactly. So the function signature of your definition has to match up with your function prototype up here. By the way, you will see sometimes people leave out the parameter names. That's perfectly fine. Doesn't make any difference whether you keep them or not. And that's really it. As long as you define your function prototypes above main or above where you're going to use them, you can feel free to define your functions anywhere you want in your code. So this allows us to put main up at the top of our file. There isn't much more to understand about this. What's really critical that you remember is what is the difference between a function prototype or function declaration and an actual definition. When someone says function definition, they mean the full-fledged function, the whole thing. When they say function prototype, it's really just the signature. So guidelines, like I've said, you can omit parameter names. So instead of int sum, int x, int y, we can just write the types. This does not, of course, mean you can leave out the parameter names in the definition. I can't leave out the word parameter here because then how would I reference it? Right? So we can optionally leave out the parameter names here, but of course not here because we're going to write code, presumably, that would use those variables. Your function prototypes must match with the definition. And here's where you can get yourself into a little bit of trouble. If you write your function prototypes and everything works, and then you change your return type, you change the name of the function, if you change anything, you must remember to change it in both places. You have to change the prototype and the function definition itself. And if you fail to do that, you're going to get some more of these what are called linking errors like we've talked about before. Think of prototypes as something that has to be sort of early on in the file, right? And they're essentially promises that you're making to the compiler. You're saying to the compiler, if I use a function called myfunction1, let it go because I will actually define this eventually. If you don't, of course, then that promise is violated and you'll get a compiler error. So really any example that we've gone throughout the list of these modules could be an example, or any example using functions at least, could be an example of where we use function prototypes. So I'm gonna take the opportunity here just to do a little bit more of a complex problem involving functions, and it's actually very similar to an example we did previously where we calculated pi. Before we get into the math here, I'm gonna write several functions to help me out with this process. And what I'll do is I'll write function prototypes for each one, just so I can make the code in whatever order I want. So programming example 26 is asking us to estimate the value of e, or actually more specifically e to the x, where x is some arbitrary value that a user might enter in. So the constant e is used in many mathematical equations. It's approximately 2.7. That's not the number we're going to get out here. We're going to get 2.7 raised to something. It's hard to calculate. It's sort of an infinite series. It has theoretically been calculated out to, boy, it looks like almost a billion decimal places. And I'm showing you essentially what the algorithm for doing that would be. As the user types in, if the user types in an x value, I can estimate what e to the x is by calculating a repeating series of numbers, or of terms. So each term is going to be added, and the user might say, well, n could be 20, n could be 1,000, n could be 900 million. We'd certainly be running for quite some time there. So I'm going to have the user enter a value of n and also a value of x, and I'm going to compute this series. So let's give a little thought as to how we would go about solving this problem. By now, hopefully, you're starting to pick up on different problem types. And this is, again, one of these classic accumulation problems. Let me bring a picture of this onto so we can draw on it. Okay. And if we look at this, clearly we're going to have some sort of a for loop, 0 through n, right? We're going to go around n times, meaning n equals number of terms. Right, so if n equals the number of terms, each term will just be accumulated. So basically we've got a compute term step, and then we have an accumulation step, which will probably be done all in the same line of code. It's this compute term that we really need to think about. And so if we look at each term, we can see that the only number that's really changing here is this value, 0, 1, 2, and 3. And we need to compute x to the third, and we also need to, or actually let me just call this I, right? If we think about I in the for loop accounting for 0, 1, 2, 3, we need to compute x to the I, and we need to compute I factorial. Right? Now, if you're not familiar with factorial, n factorial equals 1 times 2 times 3 times 4 all the way out to n. Right? So the factorial is actually quite a large number. It's very similar to the summation, but we're doing multiplication. So there's sort of these hidden jobs here, right? So we've got to compute an individual term, but at the same time of computing that term, we've got to call the power function, and we've also got to compute the factorial. So my first step in any of these problems, of course, would get the 0, 1, 2, 3, 4 to maybe print out to the screen, ensure that I've got a for loop that works correctly, and then we'll go about computing a term. And I'm going to make this an actual function to compute the term, given an I value. So let me bring up Visual Studio. Okay, and so what I've done just ahead of time is write the simple prompt statements to get e to the, or the x value for e to the x, and to get n. And the first thing that I'm going to do is I'm actually going to write a function that accepts those two values and produces the estimate. Rather than putting that all in main, I'm going to create a separate individual function for that. So I might have something like this: e to the x equals estimate e to the x, where I pass in the value x and the value n, and I can call that function. And now I'll just print out the estimate equals that. Right? So traditionally we would always write this function estimate e to the x all the way up top. Instead, I'm just going to write a prototype first. It obviously returns a double. It's going to return the estimate of e to the x. Estimate e to the x. It's going to accept a double and let's say num terms. Okay, and I'm just going to put that as a prototype. Below main, and it's kind of nice to have main up at the top. Below main, I'll have the full implementation. So in estimate x is where I'm going to actually go through and employ this entire series of calculations. All right, so to estimate x, I need to calculate num terms. So I'll start with a for loop, I less than, and I'll go all the way up through num terms. If we look at the example, that's how it's sort of been written. If we, n represents the last term, so it's actually, n plus 1 terms. So we'll go through num terms, I plus plus, and right now I'm just going to print out term for I. And for now, I'm just going to return a 0 just to get things to compile and start to run. So I've got my main program that's going to ask the user for stuff. I'm going to call my estimate e to the x. My estimate e to the x is woefully incomplete so far, but at least it's a little bit of a start to get us going. Build. And we'll run this. enter a value, and again, it doesn't really make a difference what value I enter in just yet. If I have 10 terms, I see I'm going to compute the term for 0, for 1, for 10, all the way through 10. Of course, my estimate ends up at 0. The important part is that I've got the numbers right, and notice that the I value for each one of these terms, the I value is what I'm printing out right here, and that's exactly the I value that I'm seeing here. Okay, so now what I'd like to do is compute the term. In each round, I want to compute that term. And I'm not going to do that all kind of tied up into the same for loop. I'm just going to stub a function out that accepts the I value and the x value and computes the term, computes the individual term. It's always x, and we're just using the 2, or the I, I'm sorry. So again, I can write my function prototype, a term, so let's call it compute term, accepts x, and it accepts I. My definition can go anywhere. I'm going to kind of put them down in reverse order. And now I'm going to compute this term. So the numerator of the term is just the x to the ith power. I is my parameter. Okay, and we'll include CMath. And there's our numerator. Now our denominator is not as easy. Okay, so our denominator is the factorial of whatever I is. And that's going to involve a loop. That's actually going to involve its own accumulation. I don't want to include that. I want to keep my functions fairly small, so I'm just going to write another function called factorial. And I'm going to pass in whatever number I want as the factorial, and it will return it to me. So I haven't written a function yet, but I know I'm going to ask for the factorial of I. And in fact, I can provide a function prototype for it. Notice I'm returning a double. And the reason I'm returning a double is that the factorial gets very, very, very big. The factorial of 20, 1,000 or something like that is going to be way above the number range of the normal integer. So because it gets so large so quickly, I'm going to plan on that being a double value. Even though it's still an integer, I'm going to use double just for the wide amount of values that I can store. For now, the factorial code, I'm just going to return 1, which is not really useful yet. But the point being is that I can now return numerator divided by a denominator, and that is an individual term. Right? Each individual term is a numerator of the x to the 0th power, the ith power. The denominator is I factorial, and I've got my term. I'm going to compute the term. And for now, let's just call, let's actually just print it out. And of course, the term won't really be correct yet because we don't have the factorial code built. But at least when I type in, let's do 5, I can see some numbers coming out. And clearly, it's really just x raised to the power. So x is 5. Raised to the 0th power comes out as 1. x5 raised to the 1st power is just 5. 5 squared, 5 cubed, 5 to the 4th, 5 to the 5th. And I'm just getting those numbers because that's all my term really is. My numerator is a power, and factorial is returning 1. All right, so let's make this a little bit better and actually compute the factorial. Right, so the factorial is just 1, or we really don't need the 1. 2 times 3 times all the way out to I. So I'm going to say my return value starts at 1. Right? This is my accumulator variable. Since I'm using multiplication, I want to start it at 1 instead of 0. I'm going to say for int I equals 2. Or actually, I shouldn't use I. Let's just call factorial of n. So for int I equals 2, I less than or equal to n. I want to go all the way through n. I plus plus, I'm going to say value times equals I. And then I'll return value. Now, when I run this program, certainly, as I start to call this with this I value is going to get copied into n. I'm going to compute the value of n. It's kind of hard for me to, off the top of my head, know what x squared over 2 factorial is going to be, or 3 squared over 3 factorial. So I might want to actually just test my functions a bit just to make sure that they work. And we can always test functions individually. So before I even think about all the rest of this code, let's just comment this out for a second. And instead of calling my estimate e to the x, I just want to test my factorial code. And I can test it with a couple of things, a couple of different values just to get the idea. So let's say factorial of 0. What does that equal? We want to make sure my code works correctly for factorial of 0. 0 factorial and 1 factorial are just defined as being 1. And let's make sure that our loop works for those. And I'm just going to call my code. And I'll compute a couple of them. So I like my special cases, factorial of 0, factorial of 1. I want to make sure that they come out as 1. Maybe factorial of 4, I can easily calculate that. Maybe factorial of 6. 60 is going to be pretty large. So notice I'm kind of backtracking, right? I'm commenting out some of my code to replace it with some really kind of straightforward sort of just testing code. Don't feel like everything that you write is going to make it into your eventual program. Lots of times we'll comment some stuff out and we'll just write some testing code just to see what factorial does. Don't feel like you're compelled to only write what you've been asked to write in a problem. Lots of times we write code to help us test. We write code to help us figure out whether our program is really working correctly. Then we just delete it afterwards. So we've got factorial of 0 and factorial of 1's coming out as 1. That's good. 4 factorial is 24. So 2 times 3 is 6 times 4 is 24. That's good. 24 times 5, let me bring a calculator here. So if we do 2 times 3 times 4 times 5 times 6 equals 720. Perfect. All right, so that's starting to look very good. So we can take this out now. We've looked at factorial code, and it seems to work. And I've included my factorial call down here in compute term. Let's give this a run and start to see what our terms would be. So I'll still do 5, and we'll do, let's say, 10 terms. So we see the first term is 1, the second term is 5, then 12.5, then 20 and 26. And so we're seeing that number sort of start to rise and then start to fall. So each term is just at that value. Now we don't know. I don't know whether those values make sense, right? So I really haven't. This is not an accurate test yet. I really am going to need to compute the accumulation, and then also maybe go on a calculator and figure out whether that value is starting to match up, and determine whether or not I've done it correctly so far. So the first thing I'll do is I'll do the accumulation. So my my value is equal to 0. This is just a straight addition accumulation problem. Value plus equals term. And at the end, I'll return value. So there's my estimate. So again, e to the 5th power, let's do 10 terms, and we come out with 146.381. So to give this a test, we can bring up a calculator online. We can do it by ourselves by hand if we want. Calculate e to the power of x. Then let's see what we've got. We've got a calculation here. If we type in 5, calculate, we see 148. And that's not bad. That's not very far from our actual result of 146. To check to see whether this is going to actually give us a good value here, maybe let's do 50 terms. And now we've got the 148.413, which is very, very close to what we're getting on this calculation here. And of course, we could check any number of calculators. We could check any number of examples, right? If we try to do 2 to the e power, or e to the 2 power, 7.38. If we enter x as 2, maybe give us 50 terms again. We're close, not quite accurate. 7389. We got 7. We're a little bit off. Maybe we can do 100 terms, and we're getting pretty close. Now, how many terms? You can see how small of a value each additional term is actually giving us. So it's not going to get that much closer all that quickly. Okay, so we've got a pretty good calculator here, and what I want to just point out is that I followed a strategy of actually breaking down each one of my functions into fairly small, fairly shallow in terms of its nesting functions. My estimate at e to the x really just contains one for loop, but it actually contains much more to it, right? Because it's got the compute term. And compute term contains a call to power, contains a factorial, and the factorial itself contains a loop. So there's a lot of power contained in each one of these functions, but they're all actually quite small. In a couple of modules from here, we're going to start to talk about what's called top-down design. And this could have been in that module, because the way I've solved this problem is in a very modular way. I've taken each individual action, the estimation, the computation of a term, the power, the factorial, each specific piece of work that I had to do, I implemented in its own small function. I've provided a nice function prototype up at the top, so I can have main still at the top. I can find out what my program generally does just by looking at the first parts of the code. And as I scroll down through my code, I get deeper and deeper into levels of detail. And ultimately, that's what we're trying to shoot for. We're going to eventually start to look at functions as always should be sort of less than maybe a dozen or so lines. And as we scroll down in our source code, we ultimately like it to get lower and lower and deeper in terms of detail. And function prototypes really allow us to do that by letting us declare these functions ahead of time without worrying about the order in which they're used.